Hello everyone, today we'll be talking about polynomials and rational functions in the first half. So a polynomial function is a specific type of function that looks like this. F of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus blah blah blah, three dots, plus a sub 1 x plus a sub 0. Let me give you a couple of examples. You've already seen this. 3x plus 1. That's linear. That's also a polynomial. 3x squared minus 4x plus 1. That's a parabola or a quadratic. Quadratic parentheses parabola. I can also take higher powers. X to the third minus 2x to the second plus 11x plus 10. That's another polynomial. As it happens, this is the idea of a polynomial. It's basically a giant plus or a giant sum where I add together a collection of elements that look like constant numbers times x to the power of a whole number. This n has to be an integer, so n can either be 1, 2, 3, etc. And the coefficients, the a's, the a sub 0 to a sub n, are fixed real numbers. So like in these examples, these are gonna be the a's. This one is going to be 1 times that, so the coefficient is 1, negative 4, negative 2, plus 1, plus 11, plus 10. That's basically going to be the a sub n's. Okay, and the x are raised to the powers of integers, where the highest power that appears in the polynomial is called the degree. So in the first one, it's just x is the highest power, so that's x to the 1. That's called degree 1. So that's degree 1 because the highest power of x is in fact 1. Now what about the second one? That's degree 2, so that's going to be degree 2 because it's x squared. The highest power that appears on the second line's example is 2, so degree 2. Degree 2. What about the third one? Well, logically, the highest power of x that appears here is degree 3. Degree 3. Good. Okay, that's degree 3. Wonderful. That is in fact degree 3. Now, let's take a look at what's going on here. The degree of a polynomial, that's just terminology. It's denoted deg f. We won't really use this kind of notation, but if you want to, you're welcome to it. But degree of f is equal to n. You can just specify it in words that the degree of the polynomial is n, assuming that n actually appears. So it doesn't count, for instance, if I do this, 0 times x to the fourth plus x to the third plus x to the second plus x to the 1 plus 1, then the degree here is not actually 4. The degree is 3. This doesn't count. So the degree is in fact what? The degree is 3, the highest power. Degree is 3. Degree is 3. Beautiful. So it must be a true power that appears, not a ghost that's just multiplied by a 0. Okay, let's talk a bit about some specific examples. The first one is special, degree 0. That's just a constant function. A degree 0 polynomial is a constant function, just a technicality. Degree 1 is the highest power that's going to show up as x to the 1, so it's just a linear function, mx plus b. Degree 2 is a quad function, ax squared plus bx plus c. That's something we have already done. It's a quadratic function or a parabola. I'm going to even specify this in parentheses. This is a parabola. And the third one is just something to just enrich our terminology or mathematical terminology. Degree 3 is called cubic, degree 4 is quartic, and degree 5 is quintic. You can forget about these. You won't actually use these words. We, in this class, will be concentrated. You will be expected to know what a linear function is and what a quad function is. You may see a polynomial of degree 3 or 4, but you won't actually need to know the terminology that they're called cubic or quartic or quintic. Just something to think about terminologically. The basic building blocks of every polynomials are these x's to the power of whole numbers, x to the n. These are just called the monomials, x to the n. These are power functions with whole numbers. Again, just something to think about. For instance, monomials are x to the 0, x to the 1, x to the 2, x to the 3, x to the 4th, blah, blah, blah. These are called monomials. mono from the word mono for one, because it's only one building block. And let me just remind you that x to the 0, in fact, anything to the 0 that's not 0 is going to be 1. X to the 0 is defined by definition as 1. That's why a constant, the degree 0 polynomial, is in fact a constant function, because it's going to be a sub 0 times x to the 0, and that's going to be a sub 0, constant. Something to remind you about, something useful. X to the power of 0 right here is going to be 1. Just something useful to think about. Okay, now let's talk a bit about the end behavior. Since a polynomial is made up of constant numbers multiplied by nice integer powers of x's, then it begs the question, well, how do we evaluate the polynomial, either with a calculator or on pen and paper? Answer is you can evaluate the polynomial at any fixed number you want. Take this f of x right here, plug in your x, your specific x, do log division, log multiplication, and the tedious arithmetic on paper, or use a calculator if you can, and you will get the value of the polynomial at every possible finite number x. Good. This begs the question then, if I know how to find the value of a polynomial at every number, that's an easy enough task for a computer or someone with enough time on their hands to do with a pen and paper if you're willing to do the long arithmetic. This begs a different type of question. Qualitatively, if I were going to predict the future, or if I wanted to look at the behavior of a polynomial if I were, say, graphing it, what is going to happen to the polynomial if I end up looking at humongous numbers? Well, here is the thing. I'm not just talking about numbers like 1,000 or 10,000 or 100,000. I am talking about what happens when I plug in numbers like 1 with 100 0 in x, or negative 1 with 100 0. What happens if I want to look at my polynomial's behavior, or what happens to the function, that what it spits out, the output, when I plug in something astronomically large, or astronomically large with a negative sign in front of it, with a minus sign, meaning negative a gazillion or negative a gazillion, as people would say in slang terms. This is what we would call the end behavior of a function. I want to describe qualitatively, not exact numbers, not a masterpiece drawn to scale. I want to get my bearings and figure out what happens to the polynomial's value as x becomes very large, positive. That's denoted infinity. This is called infinity and is denoted like this, with a flipped over 8. Why is this actually, what does this actually mean? Infinity means greater than any number you can think of. Greater than any number you can think of. You can think of. So if I play this silly little game where I'm playing against an opponent, and the rules say that my opponent has to give a humongous number, and my job is to find something bigger, well, that game is already won on my end from the beginning. If my opponent says 1,000,000, I'll say 1,000,001. My opponent says 10,000,000, I'll say 10,000,001. My opponent says 1,000,000,000, I'll say 1,000,000,001. You can see where I'm going with this. No matter what number you can think of, you can always think of a number that's larger. This is the idea of infinity, this flipped over 8. It means greater than any conceivable number you can punch into your calculator. On your calculator, you can punch in numbers, usually, if you take an old school calculator, not too sophisticated of a scientific one. So if you have these old school calculators and you actually punch in numbers, what you can punch in are just numbers. Infinity means it's larger than any number in the universe. Larger than any old number you can plug into your calculator. Million? 10 million. 10 million? 100 million. A billion? 10 trillion. 10 trillion, whatever. That's the point. Since numbers go on forever, this thing is already possible. And as it happens, we can actually look at the negative counterpart to this, like as if it were just a 1 versus negative 1. If I have this infinity up here, where this stands for a gazillion, basically as large as I want, the negative a gazillion, what is that going to amount to? That is going to be smaller or lesser or less than any number you can think of. Less than any number you can think of. Less than. Basically infinity with a minus sign. Negative a gazillion. You can think of. Good. Now, that's the thing. Since a polynomial doesn't have any danger of violating the cardinal rules of this course, namely in a polynomial there is no division, so there is no danger of dividing by 0, and there are no roots, so there is no danger of taking the root of a negative number, I am free to plug in whatever I want into the polynomial. The domain is everything. The domain is I can literally plug in anything. Now this begs an important question. If I can plug anything, I can plug something as large as I want and as small as I want. Okay, then what exactly dictates the behavior of the polynomial? For instance, let me give you a little example. So for example, if I have x squared minus x, and I want to plug in something humongous like a gazillion, or basically I want to look as x goes to infinity. This arrow says x goes to infinity, or x blows up or grows as humongous as you would like. The question remains, what is this polynomial going to look like? On the one hand, if I take a gazillion and I plug it into x squared, it's going to look like, well, something humongous, very large. Very large, meaning infinity in its own right. If I take a trillion, it's going to grow even larger. It's going to be even more humongous. On the other hand, what I do here is negative x. So I want to subtract something from this that's something humongous. So on the one hand, we have infinity, and here I have minus infinity. I'm subtracting from this. So it seems like there is a tug-of-war going on here, kind of like a war going on between these two contradicting building blocks. The x squared goes to a gazillion, and the negative x goes to negative a gazillion, and they're pulling the polynomial towards opposite ends. One wants to go in the positive direction in the humongous way, and the negative wants to go in the negative direction. The question is, which of these actually wins? What dictates the behavior of the polynomial? It turns out that when we were talking about the degree of the polynomial, the highest power, that wasn't just something to think about terminologically or something you're going to have to put up with. That's actually something useful. If you take a look at the highest power is the dominant term, which dictates the behavior as x gets very large or very negative. In that sense, I mean negative a gazillion. There is no nice way to put it verbally, or at least none that I can think of. That's what I mean by infinity and negative infinity. So the dominant term is in effect what dictates this stuff. Okay, now let's take a look at this. For instance, in this case, the dominant term is what's going to make the polynomial behave itself as x goes to something like a gazillion or negative a gazillion. Okay, well, let me ask you a little something. If x goes to a gazillion, then I might as well just look at this. Infinity to the power of 2, think of it like 1 with a whole bunch of zeros times 1 with a whole bunch of zeros. What am I going to get? I am going to get 1 with a whole lot of zeros. So that's going to be infinity. That's what I mean by infinity. If I have negative infinity squared, that's going to be negative 1 with a bunch of zeros times negative 1 with a bunch of zeros, and that's going to be 1 with a bunch of zeros because 1 and negative make a positive. Okay, so in effect, the dominant term, the highest power, is what's going to dictate what the polynomial actually looks like as x goes to infinity or minus infinity. This is going to be basically the polynomial as x becomes large enough or small enough in either end of the number axis. That's what's going to dictate what the polynomial looks like, and it's going to overlap or start to become indistinguishable from its highest power. Let me give you a little example with Desmos. Notice, if you will, this example. The red curve is x cubed minus x squared, and the blue curve is just the dominant term, the x cubed. Notice, if you will, that as x is too small, then we see a clear distinction between the two graphs. The two graphs, the blue and red, do not overlap. So in effect, what we see happening here is as x becomes larger and larger, or smaller and smaller, we can see that the graphs start to overlap, meaning the x cubed minus x squared, this one is starting to look a lot like its higher power, which makes sense because as x becomes humongous or negatively humongous, then this x cubed is what's going to make all the difference, and x squared is going to become negligible. That's why the graph is going to look like x cubed. Good. And let me actually put this in graphical terms if you want to imagine a real number line. The numbers that we work with in this class look an awful lot like a line of numbers. That's 0. And to the right we have the positive end, and to the left we have the negative end. So here we have the positive numbers. And what I mean by infinity is what happens when I look all the way to the far right. Not a million, not a billion, not a trillion, not a quadrillion, but one with a whole lot of zeros, more than I'll ever count in the known universe. Same thing for this guy right here. Negative infinity is going all the way to the far left. And here you have an illustration in these graphs, this one and this one. You can see two illustrations of graphs of highest powers that are even and odd. Even ones look like the ones on the right, left, and odd powers look like the one on the right. And as you can see, the even powers on the left, they actually look like these kind of smiling parabolas. And that makes sense actually, because we already know that x squared is actually going to look like this smiley parabola. It's happy. On the other hand, x cubed looks a bit like this. The x squared and the even powers cannot be negative. The x cubed and the odd powers can be negative, which is the point of odd powers. That's basically what we want. Okay, so we have this right here. Now let's talk a bit about two distinct cases. What happens when the polynomial's degree n is even versus what happens when it's odd. So for instance, if n is even and your an is positive, then you actually take a look at the dominant power. So in the first case, it's going to be an times x to the power of something even. This is always going to be positive. This is always going to be positive. And we have already said that a sub n is already positive. We have already agreed on that. Positive. Positive times positive is always going to be positive. So always positive. Good. That's the point of an even power. It doesn't really care. It's oblivious to the minus sign. That's why when I plug in a gazillion or negative a gazillion, the function will spit out a gazillion, a positive gazillion. What about the bottom one, when an is negative and the x sub to the n, the dominant, the highest power is even? Then for this case, I have an times x to the even. Now the x to the even is always going to be positive, and this thing is going to be negative. Negative times positive is always going to be negative. Let me separate these out. Sorry for the crammed handwriting. So this is always going to be negative. In other words, what I'm going to do is when I plug in a gazillion or negative a gazillion, that is going to end up like negative a gazillion. That's what we mean by this. Something positive times something positive right here where the cursor is pointing is going to be positive, and something negative times something positive is always going to be negative. Okay, and that's the point of an even power. It doesn't make a distinction. Now, let's take a look at what happens for case B when n is odd. So for x to the power of n, which is odd, remember, odd powers like x to the third, for example, x to the third, or x to the fifth, or even just x to the 1, for instance, which is just x, these distinguish between signs. Infinity to the power of odd is going to, infinity to the power of odd is going to be infinity. Think a million or a gazillion or one with a bunch of zeros. If you have trouble or if you find yourself needing something to hold on to when you're actually thinking of infinity, think one with a whole bunch of zeros. So one with a whole bunch of zeros to the power of odd is going to be, well, infinity. So one with a whole bunch of zeros positive still. Now what about negative infinity to the power of odd? That is going to be negative infinity, for instance, negative 1 with a whole bunch of zeros to the power of odd. What is that going to be? It's going to be negative 1 with a whole bunch of zeros. So it's going to be negative. Unlike the even power, the odd power can be positive and negative. So that's why the thing that calls the shots is not just what I plug into it, but also the coefficient right here. If an is positive, then here we have negative times positive makes negative, and positive times positive times positive makes positive. If I have a to the a sub n is negative, then I have infinity when it's negative because the negative cancels the minus sign, and here we have positive. Or here we have negative, sorry. Again, this is just the idea. Let me give you an example. Negative x to the fifth plus x to the fourth plus x to the third, for instance, just an example. So the dominant term is negative x to the fifth. Okay. So if we actually take a look at this, the dominant term is negative x to the fifth, literally the highest power and whatever number is multiplied by it, in this case the minus sign. So we have this little guy. And so negative x to the fifth. So what happens as x goes to infinity? As x goes to infinity, you get negative infinity to the fifth. And we have already said, what is infinity basically? It's negative 1 with a whole bunch of zeros, blah, 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 to the power of 5. So that's going to be negative 1 with a whole bunch of zeros. And that's going to be negative infinity. Okay, now what happens if x goes to negative infinity? Then that basically means that it's negative infinity to the fifth. And so that's going to be negative 1 with a whole bunch of zeros to the fifth. And that's going to be negative 1 with a whole bunch of zeros. Negative makes a positive. So 1 with a whole bunch of zeros. And that's going to be infinity. Good. So we have this polynomial goes to infinity when x is, so this function basically blows up to something humongous as x becomes negatively humongous, and goes to something negatively humongous when x goes to something humongous. Or if you want to look at this function on Desmos, I can actually show you right now. Just let me change the window. This is basically what this function looks like. As you can see, when x is becoming negatively small, like negative a gazillion, this thing is shooting upwards and becoming humongous on the y-axis, or the value that it spits out. As x becomes positively humongous, then the function starts to go down uncontrollably up until it reaches, well, a never-ending bottomless pit. So that's over and done with. Now let's talk a bit about rational functions. Well, polynomials are some of the simplest functions and the ones that are most conveniently used to study calculus because you can do operations on them quite easily. When we talk about derivatives later on, we can see that doing derivatives and calculus with them can actually be a pleasant experience because they're so fun to work with. Now let's talk a bit about how we can actually take polynomials and make them slightly more complicated. That's where rational functions come in. A rational function is a ratio of two polynomials, meaning polynomial 1 divided by polynomial 2. So polynomial 1 divided by polynomial 2. Good. And remember that we must not divide by 0. So we must not divide by 0. Must not divide by 0. Okay. So let's talk a bit about the end-term behavior of a rational function. If I have a polynomial divided by a polynomial, what's actually going to happen when x goes to a bazillion or negative a bazillion, or more formally infinity and negative infinity? We've already talked about the polynomial case. If I just have a polynomial, not a fraction, then I know to look at the highest power along with the dominant term, that is, and I know that that dictates the end behavior of the polynomial to the far right or to the far left. Good. Now, logically, intuitively, what we would expect is that this type of thing for a rational function is going to generalize. What dictates the long-term behavior, or in this case, the behavior at infinity or negative infinity, or think of it as a gazillion and negative a gazillion, for a rational function is going to be the highest power on top divided by the highest power on the bottom. So what dictates the end behavior of a polynomial is going to be the highest power on top versus the highest power on the bottom. That's logical. Instead of a highest power, we have a fraction of highest powers. That's easy enough. Now let's take a look at what happens when the numerator is clobbering the denominator. When the numerator dominates, in other words, I have something like x cubed plus x squared minus 1 divided by x squared plus 1. Here I have x cubed, and here I have x squared. The numerator dominates. In this case, this thing is going to be dominant. The x cubed divided by x squared is going to be dominant. In this case, what the polynomial will look like is x cubed divided by x squared, literally the highest power on top, divided by the highest power on the bottom. What is x cubed divided by x squared? It is just x to the power of 3 minus 2. Subtract powers. That is just x. Well, this x, as x goes to infinity or negative infinity, if x goes to a bazillion, this thing x is going to go to, well, a bazillion, or negative a bazillion if it's negative. In this case, the polynomial, or the rational function, I should say, goes on to the far left or to the far right in its value. Basically, it grows uncontrollably large or uncontrollably minuscule with a negative sign. Good. What happens if there is a perfect balance? For instance, for case number 2, if I have x squared plus 2 divided by 2x squared plus 1, then I am going to take the dominant one on top divided by the dominant on the bottom. Notice they're parallel. I can sort of enclose them in this ellipse that's symmetric about them because they're of the same degree. So in this case, it's going to be x squared divided by 2x squared. That's this one. Kill these, and you're left with 1/2. In other words, I get a number. Meaning that in this case, we actually have a function, a rational function that's actually looking like it's approaching a finite number. Let me give you a little example with Desmos. If you actually take a look at this function on Desmos, this function kind of has this hump. We won't talk about this for now, that's irrelevant. But if I look all the way to what happens when x becomes humongous, or negatively humongous, we can see that the y value, the function, in terms of the y-axis, is starting to look an awful lot like a constant function. It's starting to trend, or look like it's indistinguishable from the function y equals 1/2. You can see the black curve and the purple curve, they're not exactly aligned. If you zoom in, you can see that they're distinct, but as you're growing larger and larger, you can actually see that they're kind of overlapping. And that is precisely the point here. So this function tends to a finite value. This is what we will call horizontal asymptote, because horizontally it looks like the function is approaching a constant number horizontally, like this. This black curve is going to be the horizontal curve, or the horizontal asymptote, as x grows bazillionly or negatively bazillionly. That's basically what we mean by horizontal asymptote. You can forget about the terminology for now. We'll talk a bit about this when we do limits. We'll talk actually a lot about this when we do limits on Wednesday. We'll have an entire lecture on limits. Okay? And what happens if the denominator dominates? For instance, let me give you a little example. What happens if, for instance, I have x plus 1 divided by x squared plus 1? Well, I'm going to take this guy divided by this guy. X divided by x squared. Kill these, and you're left with 1 over x. What happens to 1 over x? What happens when I take 1 and I divide it by a bazillion? What happens when I divide 1 by a million, or a trillion, or a quadrillion? I basically keep moving the decimal and keep padding the number with zeros to the left. What's going to be happening here effectively is I'm going to get a fraction so small that it's going to tend to 0. That's why this polynomial is going to actually look an awful lot like 0. Gets closer and closer to 0. This gets closer and closer to 0 as x gets larger, very large, or negative, or very negative. Think of it like this. Take your scientific calculators and do this little experiment. 1 divided by 1 with a whole bunch of zeros. That's going to be approximately, that's going to look like almost 0. Is almost 0. Even with a negative, who cares? It's going to be negative something close to 0. It's still going to be pretty close to 0. And if you want to see this example on Desmos, let me show you right now. So if you actually take this example and put it in Desmos, what you see happening here is the red curve, where the denominator has a higher power than the numerator. What you'll see happening is the red curve is actually starting to look like, as x becomes larger and larger, or smaller and smaller, it's going to get an awful close to the value y equals 0, which is in blue. That's why the value of the polynomial is going to actually approach 0. That's a specific case. Again, 3 rules. Please be familiar with them for what happens to a fraction. of powers of x's. Basically, that's the rational function. Either the numerator dominates, it's a higher power, or there's a perfect balance, they're equal, or if the denominator dominates. So three distinct cases, please be familiar with them. Okay, now let's talk a bit about what happens to the rational function when I near points where the denominator is 0. If the denominator is 0, I have a problem. I cannot plug in a point x that makes the denominator 0. That would be undefined. We must never ever divide by 0. If you try to plug in a division by 0 into your calculator will complain about division by 0. So this actually raises an important question. I can't actually plug in something that makes the denominator 0. I can't divide exactly by 0. But what happens when I plug in a point that's very, very close to 0? What happens to the value of the function then? Does it grow haywire, or does it actually look like something sensible? For instance, take 1 over x. This is the example, this one, and I'm getting very, very close to the problematic, the no-no point. I cannot plug in x equals 0 exactly into f of x equals 1 over x. I must not divide by 0 exactly. But what happens if I divide by something that's very, very close to 0? What happens when I do 1 divided by 0.00001? Or 1 divided by negative 0.00001? I can get close to the no-no point either from the positive direction or from the negative direction. The no-no point is x equals 0. So if I plug in something very minuscule but close to 0 but positive, that's this one right here, what am I going to get? I'm going to get something very large. Very large. And if I do this, I am going to get negatively large. Meaning if the top one was something like 1 with a whole bunch of zeros, this is going to be negative 1 with a whole bunch of zeros. In other words, for this particular function, what we have, if you actually plot the graph of this little function 1 over x, is you're going to see this. This is the graph of 1 over x. Graph of 1 over x. So as you can see, when I get close to the point 0 from the right, I have this. The function is hitting kind of a vertical wall. It's basically growing haywirely large. And in this case, it's going negatively large depending on the side. To the right, it's positive. To the left, it's negative. That's the two bubbles circled in green. This is what we call a vertical asymptote. Let me show you on Desmos. If we actually take a look at what's going on as x becomes closer and closer to 0, either positive small fraction or negative small fraction, we can see that the function is shooting upward. The green curve, the 1 over x, is shooting all the way up with no end in sight. You can actually zoom out and you can see that there is no end to this. This is what we mean by a vertical wall. A vertical asymptote, to be more mathematically precise. We'll talk more about this when we do limits. But that is exactly the point. The function is starting to look like a vertical kind of tidal wave. It's crashing vertically on top of this. That's exactly the point. So the function is actually going up to infinity here. It's going haywirely large, and growing negatively large here. It's going haywirely negative. It's going down all the way to this bottomless pit. That's what we mean by a vertical asymptote. The graph, when we talked about a horizontal asymptote, that's what happens when we look all the way to the far right or to the far left. It's starting to look like a constant value. In this case, it's starting to overlap with the horizontal y equals 0. In this case, it's actually starting to overlap with the vertical line x equals 0 in black, or the y-axis. That's basically why we call it a vertical asymptote. That's what we mean by a vertical wall. Okay, now, the thing that remains is, what happens? Are all functions going to behave this way when I have a no-no point, so to speak, and I get near the no-no point? Are all functions going to grow haywirely large or negatively humongous with a negative sign as I approach the no-no point? Or can there be some functions that are only problematic at the no-no point, but near the no-no point actually behave themselves? This is the debate of a vertical asymptote versus a hole. If we talk a bit about vertical asymptotes, this occurs when the numerator is not 0 and the denominator is. So if your numerator is not 0 and the denominator is 0, let me actually use blue, sorry. If you have non-zero divided by 0, that means the function is growing haywirely large or negatively large, and that's why it's hitting kind of a boundary wall. So non-zero divided by 0, that's going to be what? A vertical asymptote. Sorry, let me adjust my handwriting. Ran out of room. Let me just change this bubble. Yeah, that's what we mean by a vertical asymptote. It's growing haywire. It's hitting a vertical wall. Think kind of like this graph of 1 over x and Desmos where it's hitting this thing vertically. This is what it looks like. This is what it looks like vertically. It's starting to grow vertically enormous. Okay, now what about a hole? A hole can only occur if you have non-zero divided by 0, in which case you're going to have to use algebra to actually simplify your fraction and get to a fraction that's actually going to reveal what's hiding in disguise. So 0 divided by 0, you are going to have to use algebra to get to where you want to be. We use algebraic identities, or the quad formula, to actually cancel common factors. And let's see a bit how we can do that with a specific example that's going to serve as kind of a warm-up example to the lesson on limits. Take a look at this function, this one in the example. X to the 4th minus 5x to the 3rd plus 6x squared divided by x squared minus 5x plus 6. Okay, let's actually factor this as best as we can. Notice, if you will, that in the numerator I can factor out the x squared. I can factor out the x squared much like this, and I can actually keep the rest of the numerator as is. So, okay, so we factored out the x squared. We can actually factor out more than that. X squared minus 5x plus 6. That's going to be x minus 2 times x minus 3. Sorry, let me just adjust the limits of the video frame, sorry. X minus 3. Okay. So if you want to factor this fraction all the way to the end, you're going to get this little guy right here. This is what you would call the most algebra we can do to actually beautify this original fraction. So the function is undefined at two numbers, 2 and 3. Okay. But what happens when I reduce the fraction? I can kill the x minus 2 on top and on the bottom, and I can kill this guy and this guy right here, and I can get x squared. In other words, wherever the function is defined, it's equal to x squared. The 2 and the 3 are undefined because of a technicality. At 2 and 3 exactly, I would be dividing by 0, which is a no-no. But near those no-nos, what I can do is I can plug in something close to 2 and close to 3 in the simplified version, which is x squared. And so if I take this and I plug in something close to 2, I am going to get something close to 4. So x close to 2, x squared is going to be close to 4. Sorry, the frame got away from me again. Close to 2 squared, which is 4. Now, x close to 3, then x squared is going to be close to, this is a very good intro to limits, 3 squared, which is 9. In other words, this graph has what you would call holes, basically points where the no-no points exactly are missing, but everything near it is just intact. So this kind of looks like a parabola with a missing 2 points, 2 and 4, and 3 and 9. So this graph is going to look an awful lot like this. Like this, and this right. So this is going to be the f of x in the example. And this is x. This is going to be 2, and this is going to be 3. This is what we mean by holes. The graph is the same as the graph of the original parabola x squared, just a smiling, smiley, happy face parabola, except that what's happening here seems to be that we are missing 2 points. 2 points where the denominator is 0, and we must never divide by 0 exactly. Near those holes, if you actually look near those holes, it's not growing haywire, it's just the same graph. So, kind of like the same graph as our normal parabola, except missing these holes on a technicality. And that's it for this half. Thank you, everyone. We'll conclude with the second half. Let's talk a bit about exponential functions. Let's talk first about exponents, not through the lens of calculus, not through functions, but plain exponents. So much like in when we talk about multiplication, a times n is, I believe, a plus a, blah, 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 plus a n times. That's what we mean by multiplication. Regular multiplication product that you're used to. Now, what happens with an exponential? A to the n, in this case, means multiply a by itself n times. Multiply a by itself n times. Beautiful. That's what we mean. This is read a to the power of n. This little guy is read a to the power of n. Okay? So for example, a to the power of 1 is just a, because you're multiplying by itself only once. A squared is going to be a times a. A to the power of 3, or a cubed, is going to be a times a times a, and so forth. Now, in the expression, this little guy right here, a is called the base, and n is called the exponent. That's the power. The power is called the exponent. So base to the power of exponent. Sorry, video frame got away from me. Move to the right, exponent. Beautiful. Now, let me remind you of two important identities. A to the power of 0 is 1, assuming a is not 0. Oh, I'll just remind you of this. We won't actually see this in this class, but just to be perfectly proper, 0 to the power of 0 is undefined. So for the purposes of this class, a to the power of 0 is 1, and a to the negative n is going to be 1 divided by a to the n. That's this guy. So taking a negative power is the same as taking a reciprocal. Good. 0 divided by 0 is undefined. That's just mathematical convention. So 0 divided by 0 is undefined. So in this class, we won't actually need to know this fact. That's not one of the cardinal rules of mathematics. You won't actually need to worry about it. And now let's talk a bit about this example. 3 to the fifths to the power of negative 2. That's this example right here. Let's talk a bit about this. That's going to be the same as 5/3 to the power of 2. Remember, when you take a negative power, it's the same as flipping the stuff over. So that's going to be 5/3 times 5/3. Again, a fractional multiplication, so that's just going to be 25 divided by 9. And that's the answer to this little example. Okay, now let's talk a bit about roots, since I was giving you a headache earlier about what to do with roots, and we must not take square roots of negative numbers in this class as a matter of convention. So in this class, we will only take roots of non-negative numbers. So let a be a non-negative, meaning 0 is possible, but not the negative numbers. That means including 0. Sorry, this extension. So in this case, can include 0. Include 0. And n is a positive integer. If n is odd, then a to the 1 over n is the unique real number whose nth power is a. What do I mean by this? If I take, for instance, 4 to the power of 1/2, that is literally the square root. Why is that? Because that's literally the number that I need to multiply by itself, or multiply twice to actually get the number 4. That is 2. 4 to the power of, for instance, 8 to the power of 1/3, that's the cubic root of 8. And that's going to be 2. Because if I multiply 2 by itself three times, I am going to end up with an 8. 2 times 2 times 2 makes 8. Beautiful. Okay. This is what we mean by an nth root. So some people prefer the 1 over n. Some people prefer square root of nth root of n. I will let you know that per the rules of this class, some people prefer either. It's up to you which to choose. A to the 1 over n is equal to nth root of a, like this. Beautiful. And if n is even, then a to the 1 over n is going to be the unique non-negative real number whose nth power is a. Okay, that's basically the same definition as above, except for a small catch, that when the root is even, when the index of the root, this n, is actually even, let me just remind you that Even roots must always be positive in this class. So the square root of 4 is only going to be 2. There is no such thing as square root of 4 equals negative 2. That's a no-no. Good. Let's do a bit of examples. Let's do a bit of an example. What is 8 to the power of 1/3? These are the examples I'm talking about. So 8 to the power of 1/3, that's going to be the number, the third root of 8. What number do I multiply by itself 3 times to get 8? That's going to be 2. What number do I multiply by itself 4 times to get 1/16? 1/16, that's going to be 1/2. Let me remind you. 1/2 times 1/2 times 1/2 times 1/2. If you actually do this, that's going to be 1/16. Just fractional multiplication. Okay? And last but not least, 0 to the power of 1/n. This guy right here. Sorry. Apologies, just had a technical difficulty. So 0 to the n right here, that's going to be 0. 0 to 1/n is 0. Because the only number that you can multiply by itself and get 0 is going to be 0, regardless of how many times you multiply by itself. Okay. We have already said it's called the nth root, and if you want the rational exponents or fractional exponents, this is the same. 8 to the power of m divided by n is the same as 8 to the 1/n to the power of m. So 8 to the power of 2/3 is going to be the same as 8 to the power of 1/3 squared. Or 8 to the power of 3/2, that's going to be 8 to the power of 1/2 cubed to the power of 3. Okay, now let's talk a bit about useful laws of exponents and powers. If you have 8 to the x times 8 to the y and you have the same exponent, that I'm talking about this one right here, then you're going to add the powers. So add exponents, add or sum exponents. You're going to add them together. Good. Now, if you have a power to a power, then you're going to multiply powers. So power of a power. Power of a power. A to the power of x to the power of y means multiply powers. Good. Okay, now what happens when you take a quotient? Instead of multiplying, you divide, you're going to subtract powers. So in this case, it's a quotient, so subtract exponents. Subtract exponents. Good. A times b all to the power of x means I can distribute the power. So distribute exponent, if you want to call it something. It's not really a standard name, but just for illustrative purposes. And the same for the next one. Only the next one is a quotient, a fraction instead of a product. So if you see what happens here, here is something to think about for why a to the negative n is 1/a to the n. I didn't really talk in detail about this in class, but for a being non-zero, you can actually see why this is happening. Why a to the negative x or why a to the negative x is 1/a to the x. Again, as long as you know that this identity holds, and you know that taking a negative exponent is the same as taking a reciprocal, that's all you will need to know. But here is a brief explanation as to why that is factually true. Okay, let's talk a bit about the scenario we introduced in class. Two separate biological populations, Pop A and Pop B, both start with an initial culture of 100 microbes on day 0. Population A grows linearly by adding 50 microbes every single day, and population B grows exponentially by doubling its population every single day. Let's actually take a look at the graph. Let's talk about population A in blue. If on day 0, the population A numbered 100 microbes, both of them did, so that's 100, halfway between 0 and 200. On day 1, it actually grew by 50, so 100 plus 50 makes 150. And on day 2, it actually grew another 50, so that's 200. If every day it grows by 50, every 2 days it grows by 100. So on day 3, it's going to be 300. Or, sorry, on day 4, it's going to be 300. Etc. And it's growing linearly, like the name implies. That means since it's growing at this kind of tempered pace, the graph is going to be tempered, and the loveliest temperedest graph we can think of is the graph of a line. Hence the word in the statement that it's growing linearly. So it's going to look a lot like this. Okay, that's pop A. Now let's do population B in green. What's going to happen? If I start out with 100 and every day I double, then on day 1 I'm going to be 200. On day 2 I'm going to be 400. On day 3 I'm going to be 800. And if I do this, it's going to be kind of a graph that grows uncontrollably large like this. So let me ask you, this is population B. And what I asked in class was, can you tell me which population is going to dominate or going to grow faster or is going to basically outnumber the other population by a sizable margin? Population B. That is what we mean by exponential growth. It's growing exponentially. It keeps multiplying. Exponential growth. And this is what you would call, or just exponential for now. We talked about exponential growth in class later on. So I'm trying to stay faithful to the lecture. So in this case, A is going to be linear. So this is going to be a linear, hence why the graph looks like a line. Okay, so if you actually take a look at this, you can actually do the numbers that we did in class, and you can actually see how we got this graph. So for population A, it's going to be 100, 150, 200, 250, blah, blah, blah. Okay, now what happens to population B? 100, go to 200, double. Go to 400, double again. Double 400 and you get 800, etc. If you actually write this down as an equation, what you'll see happening here is an exponential function. This brings us to the definition of an exponential function. An exponential function is a function of the form c times a to the x, where as a matter of convention, c is called the initial value. Why is that? Because when I plug in 0, f of 0 equals c times a to the 0. A to the 0 is just equal to 1. So c times 1 makes c. That's called the initial value. And it's not 0 because otherwise the function would be boring. If c were 0, the function would be everywhere 0, and we would actually not need to worry about it because 0 is a simple function and we've already established what that is. And the base a is going to be positive. In this class, the base a is always going to be positive and not 1. Because if it were 1, it would be boring. 1 to the x would just be 1. So 1 to the x would just be 1. So boring. We want to keep the exponential function reserved for something worthy, something that's actually something different to study. If this were actually just 1 times c, it would just be a constant c. Okay, now let's actually take a look at this scenario. For linear growth, which the linear function is mx plus b, then that's basically the absolute change per unit of time is actually constant. What we mean by this, the next step involves adding a fixed number. So we start out with 100 like this, and we add to it 50, plus another 50, plus yada, 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 a whole bunch of 50s. After t days have passed, we take the initial 100 and we add 50 times t, meaning 50, 100, plus 50, plus 50, plus blah, 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 50, t times. On the other hand, in the case of an exponential in this scenario, we're not adding a number of elements to our population, we're multiplying our population. So in this case, it's going to be 100 times 2 times 2 times blah, blah, blah times 2t times. And remember, when I multiply a number 2 by itself t times, that's called t to the power of 2. That's how we got this little guy right here. Versus the one up there, versus the one in blue, that's much more modest. Moral of the story, when something grows like an exponential, it will really outgrow any line. That's going to be a lot larger. Okay. In other words, we kind of have this idea of what the graph of 2 to the x looks like. It's kind of growing like a wedge. And I did talk about this in class. I wanted to bring this up. Unlike power functions, where x to the power of n, so be cautious, so careful. X squared, x to the power of 2, is not the same as 2 to the x. Okay? X to the power of 2 is not the same as 2 to the x. This little guy right here has a variable to the power of a number. This little guy right here has a number to the power of a variable. Do be careful. Do not mix the concept of a power function, that's a power function or a monomial or a polynomial, with an exponential function. Exponential means number to the power of x. And we'll get to the graphs of what these actually look like. If you want to plot graphs, let me actually show you something on Desmos. If we actually take a look at Desmos and we take the graph of 2 to the power of x, that's the red curve. As you go all the way to the left, to the far left, as x is minuscule, like negative a million or negative a gazillion, it's going to start to get close and close to 0. As you jack up your x, as you increase your x, the y shoots up and the graph shoots up all the way until it blows up to something humongous with no end in sight. Now, how about this little guy? 1/2 to the power of x, that's the flipped over version of the graph. You can see that they're kind of reflections of each other. In this case, the blue curve is 1/2 to the power of x. So that's basically looking an awful lot like 1/2 to the power of x. So it does the opposite. It starts out, as x is minuscule, it starts out growing, it starts out humongous, and then descends and goes all the way to something that's close to 0. Let me actually point your attention to why that is. For example, red is not a good color for this. Example, 2 to the power of infinity is going to be 2 times 2 times blah, blah, blah. So that's going to be infinity. It's going to be something humongous. Right. On the other hand, 2 to the negative infinity, that's going to be 1 over 2 times 2 times 2. So it's going to be blah, blah, blah. That's going to be 1 over something humongous. Forgive me. And that's going to be something close to 0. Almost 0. That's for a greater than 1. That's when a is something positive greater than 1. On the other hand, what happens when I take an a that's a fraction? What happens then? Well, in this case I have, let's see what happens when I take 1/2 to the power of infinity. It's 1/2 times 1/2 times 1/2 times endlessly. If I keep multiplying a fraction by itself, every time I multiply by a fraction, I'm getting smaller. So in this case, it's going to be almost 0. What happens if I do 1/2 to the power of negative infinity? It's flipped over the half, and it's 2 to the power of infinity. Remember, taking a negative power or exponent means flip it over. That's why we get 2 times 2 times 2, and blah, 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 something infinite. That's what we mean by this. 1/2 to the power of negative 1/2 to the power of negative infinity is going to be something humongous. That's why this graph, 1/2 to the power of something very small, as x grows smaller and smaller up until negative a gazillion, the y value becomes larger and larger. Whereas as x grows uncontrollably large, the graph is almost indistinguishable from 0. If you zoom in hard enough, you can make a difference, spot a difference between this and 0, but as you zoom out far enough, you won't see it. On the other hand, the graph of the reciprocal exponential 2 to the x is basically the flipped over version. That's over and done with. Okay? So, yeah, if we actually talk a bit about, we have already seen what the graphs look like. Now, here is a reference with the number e that we did talk about, but I will talk about it later when we do continuous compounding. Again, e is just a special number that you don't really need to know where it comes from. It's basically a counterpart to pi. It's one of the 2 special numbers we will use in this class. So let's talk a bit about exponential equations. The following principle allows us to solve exponential equations. If I have a to the power of x1 equals a to the power of x2, this one, then if the bases are equal, then that means x sub 1 equals x sub 2. So if I have an equality where the base holds and the 2 powers, where I have an exponential equation where the 2 bases are the same, a has to be equal to a, the same base, if I have the same base, then the powers must also be equal. The powers must also be equal. That's the idea. Good. And here are the graphs for reference, but with an e, it doesn't really matter. I'll talk a bit about this after this. Okay. Now, let's actually talk about how to solve these exponential equations that we did in class. Here we have 5 to the power of 2x. That is equal to 5 to the power of 3x minus 2. Let me double underline in green the equal 5s. The bases are equal, so the bases are equal. So the base 5 is equal across, and for both is equal. For both sides of the equation. So the powers must be equal. So the powers must be equal. So 2x has to equal 3x minus 2. Subtract 2x from both sides and you'll get 0 equals 3x minus 2x minus 2. That means if I move, let me actually adjust this. Sorry, I'm going to have to pause. So what we have seen is after we subtracted 2x from both sides, we got 3x minus 2x minus 2 equals 0. So x minus 2 equals 0. Add 2 to both sides, and what do you get? Sorry, got away from me. So if you add plus 2 to both sides, what do you get? X equals plus 2. So x equals 2 is the only solution to this equation. Now, let's talk a bit about the equation below it. This one is actually going to end up with 3 to the x squared equals 9. So 3 and 9 are not the same base, obviously. 3 and 9 are two distinct numbers. How can I transfer 9 to the common base 3? I can do 3x squared is equal to 3 squared. Remember, 9 is equal to 3 squared. Good. So x squared, now we have the same base. Let me double underline it. So x squared is equal to 2. And what are the two solutions to this little equation? This means x is equal to square root of 2, which no one expects you to know the decimal of this without a calculator, or x equals negative square root of 2. Okay? Let's talk a bit about the next one. The next one is 25 to the power of x equals 125 to the power of x plus 1. Okay. Well, the 25 and the 125 are not equal, but let me remind you that 25 is actually, sorry, stylus keeps getting away from me. So 25 is actually equal to 5 squared. And 125 is actually, because 5 times 5 is 25. 125 is 25 times 5, which is 5 times 5 times 5. So just a reminder, it's 5 to the third. So it's going to be 2 to the power of, 5 to the power of 2 on the left. That's the 25, this little guy right here. Equals x is equal to 125. So that's going to be 5 to the power of 3 to the power of x plus 1. Remember what we did when we have a power of a power? We multiply the powers. We multiply this and this, and we multiply this and this. So 5 to the power of, let me actually get rid of the arrows just so they're not cumbersome. They're just a part of my visual explanation. So here we have 5 to the power of 2x is equal to 5 to the power of 3 times x plus 1. So that's going to be 5 to the power of 2x is equal to 5 to the power of 3x plus 3. And so in this case, what you see happening is if you get 2x is actually equal to, now we can actually equate the powers because the 5 on both sides is one and the same. So what you see happening here is actually 2x is equal to 3x plus 3. Good. Now, how do we actually get this? We subtract 2x from both sides, and you get 0 equals 3x minus 2x plus 3. And this is just an x, so I have x plus 3 equals 0. And if I subtract negative 3 from both sides, I will just get x plus 3 minus 3, which they cancel, is equal to negative 3. X equals negative 3 seems to be the only solution to this equation. And it's a very good one. You're welcome to check this out with your scientific calculators. Okay, the last one we didn't do in class, I did something like this one on the YouTube video. It's a very good example to go over. Now, let's talk a bit about compound interest, basically where math starts to get dollar signs in front of the numbers, so some people may find that interesting. So suppose we invest a principal amount P, that's the initial amount of money you park in a money-making account that bears interest, at an interest rate R. Suppose that's the yearly rate, so the bank might say something like you get 5% interest per year or whatever. And interest is compounded yearly. That is to say, once a year. Well, how do you actually compute how much money you'll have at the end of 1 year? Well, this is this bullet point. You will have just one principal, and you will add to the principal the interest that you earn on your principal. So your original money plus P times the interest rate R. So you'll get P times 1 plus R. That's after 1 year. If you repeat this exercise after 2 years, you will take the amount of money that you have at the end of year 1 and you will earn interest on that. And after you clean it up a bit, you get P times 1 plus R squared. If you do this at the end of 3 years, you will get this. And if you do this after T years, where T is a general variable, then you will get this. This is basically what we mean by compounding annually. The fact that it's an R and it's not split. This R happens just once a year when the bank pays you interest once a year on your money, and it's compounded for T years. That's the T up here. Good. Now, if the interest is compounded M times a year, then R divided by M is the interest used every time. The bank isn't going to give you, like, let's say the bank tells you, I'm giving you 4% interest, and that interest is compounded 4 times a year. Then the bank isn't going to actually give you 4% 4 times a year for 4 times 4, 16. No, that's not going to happen. What the bank is going to do is they're going to take the yearly rate 4% that we talked about, and they're going to divide it by 4. If you divide the 4% by 4, that means you use just 1% interest every compounding period. So you're going to take the R and divide it by the number of times of compounding a year, like this. That's the interest rate used every time it's compounded, because the yearly interest rate R and the number of times the interest is compounded is basically, and the number it's compounded, it's going to be M times T. So for instance, if I am compounding M times a year for 1 year, I'm going to be compounding M times. But if I'm compounding M times a year for T years, I'm going to get M times T, this little guy. So if I'm compounding 4 times a year for 3 years, I will get 4 times 3 makes 12 compounding periods. This is where this little compound interest equation actually comes from. So if you actually take a look at this compound interest equation, and you take a look at the simplified version where M equals 1, this is basically that. This is basically the special case M equals 1. But for a general M, then this is the equation right here, the one highlighted like this. That's going to be this. So that's going to be the R divided by M is the introduction of the interest rate being split across M cycles. And the MT is going to be this T actually multiplied by M. So that's over and done with. Now, let's actually see how to use this in real life, preferably with a calculator. How much money will we have if we invest 1,000? So that's your interest. That's your principal. P equals $1,000. R is 5%, so it's 0.05 percentage. This needs to be converted to decimal. I will make it a point to say that R in these formulas, sorry, video bounds got away from me. R in these formulas is a decimal. Good. R in these things is a decimal. So we have this. And that's your interest rate, and it's compounded quarterly, meaning 4 times a year. So your M is actually equal to what now? To 4 for 10 years, and T equals 10 years. So how much money will you have? You will have A for amount. Final amount is going to be 1,000 multiplied by 1 plus 0.05 divided by 4 to the power of 4 times 10. Four times 10. And I'm going to be using a scientific calculator to evaluate this. No one would expect you to know what this is decimally without a calculator. So A equals. So if I do the scientific calculator computation, then I am going to get 1,600. 1,000. Sorry, the stylus got away from me. Just bear with me for 1 moment. Sorry. Then this is going to be 1,643 and 61 cents if I round to 2 decimal places, or maybe even 62 if I want to round that up to nearest cents. So that's basically how much money I will have in my bank account. $1,643.62 approximately. No one would expect you to know what this is decimally without a calculator. Okay. Now, let's talk a bit about continuous compounding. We talked about the more realistic equation up there when the bank gives you interest 4 times a year, for instance, or even 12 times a year. Maybe it's a generous bank. But let's take a look at what happens when I invest just $1. I'm going to deposit $1 for the purpose of this little thought experiment into a theoretical bank account that offers a whopping 100% interest. So R equals 100. R equals 1.00. That's 100% as a decimal. Okay, so if I do this annual interest rate, and R equals 1, right? So the standard formula for our total balance after n years, since it's going to be for the n compounding periods, is going to be 1 times 1 plus 1 over n to the power of n. That's going to be basically this formula. Now the question remains, let's push it to the limit, so to speak. Let's do a little thought process. What happens if the bank is very generous? It's not going to compound n at 4 times a year. It's not n equals 4. It's not even going to be 12 times a year. It's going to compound every waking moment of every instant, so to speak. So in this case, the bank is going to be compounding every single time. Its computer is going to keep running, and it's going to keep compounding. The question remains, how much money will I have? Or what will I end up with? Will I end up with something like trillions of dollars from this $1? Let's actually fill out this table and do this little formula. So I'm going to take a quick pause and fill this out with my scientific calculator. Just bear with me, please. So as you can see, I took a few moments to fill out this table with my scientific calculator. This is just for illustrative purposes. This is not actually relevant for an exam, but it's still good as a thought process to know where this stuff comes from. So in effect, as I keep blowing up my my compounding period from annually once a year to semi-annually twice, quarterly n equals 4, monthly n equals 12, daily n equals 365, hourly n equals 8,760. As I keep blowing up the n to something humongous or infinity per the last line, I am not getting trillions of dollars. I am still getting at most something less than $3. I am going to get something like 2.71 something. And that is exactly what we mean by continuous compounding. When the bank is generous enough to compound every waking moment of every single instant, your initial deposit, you will not become a trillionaire. Okay? In other words, what you will end up with is something very tempered. And this is basically where the number E comes from. The number E, Euler's number, is a special mathematical constant. It's a special mathematical number along with pi. So E is another special number, much like pi. And E is approximately equal to 2.71 something. You don't need to know the decimal for an exam. You just need to know that E is a number that exists and is a number greater than 1. Okay, so E is approximately 2.71 something. Good. It can't hurt to know the decimal representation or put it on your formula sheets. So how do we actually get the number E? You take this little experiment with continuous compounding. As soon as you take 1 plus 1 over n to the n, this little guy, and you blow it up the n to infinity, forget about the limit for a bit. I'm going to put this in a dotted bubble because we will talk about limits in an entire lecture. That's basically what we mean by the E. The way to get E is to fill out this scientific table. The E is the amount of money that you will end up with if you park your $1 in an interest-bearing account where interest is compounded every waking moment non-stop. This is what we mean by continuous compounding. And if you actually take a look at the continuous compounding formula and actually take this, what we mean by this is basically take the continuous compounding formula. Other words, take this. This is the continuous compounding formula. Take this and convert it to E. So convert to E. So what used to be P times 1 plus R over M to the power of R times T is going to end up with as P times E to the power of RT. That is what we mean by continuous compounding. Continuous compounding. Good. That's what we mean by continuous compounding. Okay. Or, as one of my students from the previous semester nicely pronounced it, this little guy, they pronounced it PERT. PERT. You will have formula sheets, so that won't be an issue to memorize. Again, nothing to worry about. Just another one of your formulas. But insofar as how we got here, this is a good thought process to actually think about before our lecture on limits, to actually make the use of that. And so far as E, I've received some questions from several people. E is just another mathematical special number like pi. So whereas pi is associated with something like circles and trigonometry, E can be thought of as associated with this finance thing. This is one way of seeing it. E is associated with exponentials. E is good for Euler because the person it's named after in honor of is Euler. It's called Euler's number, spelled with an E. And it's also good for E as an exponential to remember that. So much like pi comes from the world of circles and trigonometry, E comes from the world of exponents and finance. Thank you so much, everyone, for watching. As always, I'll be uploading this to YouTube, and I will see you soon in class or in office hours. As always, please don't hesitate to reach out if you would like to meet on Zoom for a tutoring session or extra office hours, or if I can help you with anything at all. Thank you so much. Take care, and I will see you soon.